Hi everyone. Let's talk about points in three-dimensional space. So I have in front of you three-dimensional coordinate system and 2 points plotted in the coordinate system. So of course these axes are drawn in accordance with the right-hand rule. So that's the positive x, positive y-axis, and this is the direction of positive z. Now these 2 points that you see, I don't think it is clear to you which octant these 2 points actually reside. So whenever you are drawing objects in three-dimensional coordinate system, what you need to be able to do is to give them a clear perspective. So this is the kind of things that you need to be able to do. So for this first point that I have right here, this is what I'm gonna do. Let's draw a line on the xy plane where the x value is 2. So that line might look something like this. So here is a line, x equals 2, and again this is drawn on the xy plane. And also I am going to draw another line where the y value is going to be 1. So here's y equals 1, and that line where y is 1 on the xy plane might look something like this. So here's y equals 1. And you can see the intersection of those 2 lines. And this point in 3D might be expressed as 2, 1, 0. X is 2, y is 1, and z is 0. So from this point, 2, 1, 0, I am going to go up, straight up, exactly 2 units in the positive z direction. Now by drawing these 3 lines, I think you are convinced that this point that I circled has the coordinates x is 2, y is 1, and z is 2. So let's try something similar for this point. Let me just clear the screen a little bit here. Now what I'm gonna do is to draw the line where on the xy plane where x is exactly 3, so that line is right here. So this is x equals 3 drawn on the xy plane, and I am going to draw the line where y value is 4 again on the xy plane. So this is y equals 4. Now just like before, from this intersection I am going to now go up in the z direction straight up, and this distance turns out to be 4 units. So again, by drawing these 3 lines to give it a clear perspective, I hope you are convinced that this point has the coordinates 3, 4, 4. So whenever you're trying to draw things in three-dimensional coordinate system, try to do something to help people understand exactly where those objects are and what the orientation might be. So now that we know how to plot points in three-dimensional space, let's talk about how we can find the distance between 2 points in 3D. So in this diagram on the left, here is the point P1, and let's say that this point has the coordinates x1, y1, z1, and this point 2, let's say this is P2, has the coordinates x2, y2, and z2. So what we are trying to do then is to find the length let's call it D, of this red segment in this diagram. Now if I come straight down from this point P2, straight down so that the Z value is exactly the same thing as P1, and plot a point, the blue point that you see on the screen. And I hope you agree with me that since I just came straight down from P2, the coordinates here should be x2, y2, and z1, since the x and the y value should be exactly the same thing as P2, except the z coordinate is going to be the same thing as P1. Now you see that the point P1, P2, and then also this blue point now form this triangle that you see in the diagram. The dashed line that you see on the xy plane is going to be the shadow that you get by dropping P1 down to the xy plane and the blue point down onto the xy plane. So the dashed line, you can think of it as the shadow of the blue line that's forming that triangle there. Now we're going to try to give this a little bit different perspective. So pretend that we're going to rotate this coordinate system to get the picture that you see on the right. So it's exactly the same object, except that the orientation is a little bit different now. So in this picture, here is the point P1, here is point P2, and the blue point that we created is right there. So now you can definitely see that this triangle is a right triangle, and suppose that you could tell that even without rotating the picture there, but now it's definitely clear that what we are dealing with here is just a right triangle. So now we can use the Pythagorean theorem to figure out exactly what the distance D has to be. So here's D, the distance that we're trying to find, and let's say that this blue line has the length L, which by the way though, since the dashed line is the shadow of L down onto the xy plane, this dashed line also should have the length L. And just so that we have the label, let's call the height of this triangle to be H. So using the Pythagorean theorem, we know that the hypotenuse D squared should equal to L squared plus H squared. So that means that actual distance D is going to be given by square root of L squared plus H squared. So now let's focus on this length L. And to do that, I'm going to just look at the dashed line, the projection of the blue line onto the xy plane, and just deal with it as the line in this two-dimensional space. So considering that these two blue points that I'm drawing here are essentially the shadow of P1 and the blue point in the triangle down onto the xy plane, I think that you can agree that this first point have the coordinates x1, y1, and this point has the coordinates x2 and y2. And using the distance formula for the two-dimensional space, this is going to be given by L equals x2 minus x1 squared plus y2 minus y1. So again, if you remember this also comes from the Pythagorean theorem, But this means that if I were to square this L, then it's going to get rid of the square root. So L squared is going to be x2 minus x1 squared plus y2 minus y1 squared. Now let's just do the value h. Now this is going to be pretty simple, isn't it? Because h is going to be the difference in height of P2 and P1. So I hope that you agree with me that h is going to be simply the difference between the Z2 and Z1. So squaring this h, you're gonna get the expression Z2 minus Z1 quantity squared. Now by putting all of these ingredients together, we get what's called the distance formula. So in terms of the coordinates, x1, y1, and z1, x2, y2, and z2, we get this long formula, x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. So this is the distance formula in three-dimensional space, and I'm gonna expect you to be able to use this, know the formula, and be able to use it. So let's finish this video by doing the simple example of how we can use the distance formula in three-dimensional space. So here I have the coordinates of 2 points given, and essentially what you need to do is to plug values into the appropriate place, right? So the first points, you have, you can think of it as x1, y1, and z1. And for the second point, this is x2, y2, and z2. So using the distance formula that we just derived, distance between these 2 points are going to be x2 minus x1 quantity squared. So that would be 2 minus the negative 1 is going to be plus 1 squared plus y2 minus y1. So that's going to be negative 2 minus 2 squared plus z2 minus z1, so that would be 5 minus 4 squared. And simplifying all that, we get, let's see, it's gonna be 3 squared plus negative 4 quantity squared is going to be 16 plus 5 minus 4 is gonna be 1. 1 squared is going to be 1. So I guess the whole thing is going to be 9 plus 16 is going to be 25 plus 1. So that's going to be 26. So in this case, you find that the distance d is square root of 26. So I hope you understand where the distance formula in 3D comes from and be able to use this formula efficiently.